Hello everyone. Today we'll be looking at EVPN. EVPN is short for Ethernet VPN. It is a next-generation all-service transport VPN solution. EVPN shuns the mechanism of learning MAC addresses through the forwarding plane as the conventional L2 VPN does. Instead, EVPN introduces the control plane. It uses an extended BGP protocol to advertise MAC address information, separating the forwarding plane from the control plane. EVPN can not only replace conventional L2 VPN technologies, but also carry L3 VPN services. It unifies the control plane for various VPN services and reduces protocol complexity. In addition, it brings the advantages of IPVPN traffic load balancing and flexible deployment to Ethernet. Next, let's look at the background of EVPN. Take VPLS as an example of a conventional L2 VPN. To prevent loops on the access side, VPLS supports the CE to PE single active mode, but not active-active mode, wasting a traffic path and causing load imbalance. In the VPLS solution, all PEs establish PWs with each other on a full mesh network to forward Layer 2 traffic. On one hand, this solution requires PEs to support a large number of connections, leading to a heavy configuration and maintenance workload. On the other hand, this solution limits the L2 VPN network scale and undermines network scalability. In addition, if a network fault occurs and is detected by a PE, the PE sends a MAC withdraw message to a remote PE. Upon receipt of the message, the remote PE removes the local MAC address and must then rebroadcast the traffic, and other PEs have Tor-learn MAC addresses on the forwarding plane. This process is time-consuming and delays VPLS convergence. To solve the problems inherent to conventional L2 VPN, the EVPN solution is proposed. The core idea of EVPN is to introduce extended BGP protocols as control plane protocols. EVPN offers the following benefits. First, traffic distribution becomes more even. EVPN uses various BGP extended community attributes to technically implement the multi-homing active-active mode for traffic load balancing. Second, it simplifies configuration and maintenance. In the EVPN solution, only BGP needs to run between PEs, reducing protocol complexity. In addition, it can use BGP's route reflector mechanism. In this way, PEs do not need to be full-meshed. The remote PE supports automatic discovery. These benefits not only simplify configuration and maintenance, but also improve network scalability. Third, fault-triggered route convergence is much faster. If a fault occurs on the network, MAC addresses are learned, updated, and withdrawn all on the control plane. Service traffic does not need to be broadcast again, and relearning of MAC addresses is not required, speeding up MAC route convergence. How does EVPN achieve these benefits? Let's explore this in more detail. Before introducing EVPN fundamentals, we need to go through the following concepts. ES. When a CE is connected to one or more PEs through a group of Ethernet links, this group of links is called an Ethernet segment, ES. ESI uniquely identifies an ES. Interfaces connecting different PEs to the same CE must be assigned the same ESI. If the ESI is all zeros, a CE is single-homed to a PE. EVI is for EVPN instance. It is similar to a VPLS VSI and is used to represent a VPN user. There are some concepts available for EVI. RD is similar to an L3 VPN RD. RDs are used to distinguish different EVIs on a PE. RT is similar to an RT in L3 VPN. RTs are used to control routes to be imported into an EVPN instance. MAC VRF table is used to store MAC addresses learned by EVPN instances through the extended BGP protocol. Each EVI has its own MAC VRF table. Next, let's look at the 5 types of EVPN routes. The extended BGP protocol defines a new address family for EVPN, known as the BGP EVPN address family. Network Layer Reachability Information, NLRI, a new concept in EVPN, is defined in this address family. EVPN NLRI defines the following 5 types of routes. Type 1. Ethernet Auto Discovery Route, which is used for load balancing, loop prevention, and fast convergence. Type 2. MAC IP Advertisement Route, which is used to advertise MAC addresses, ARP entries, and IRB routes. Type 3. Inclusive Multicast Ethernet Tag Route, which is used to generate the BUM forwarding table. Type 4. Ethernet Segment Route, which is used to generate an ES member list for active-active redundancy. Type 5. IP Prefix Route, which is used to advertise IP routes. Let's look at EVPN classification. Based on the types of public network tunnels on which EVPN depends, EVPN technologies include EVPN MPLS, EVPN VXLAN, and EVPN SRv6. Based on the types of services carried by EVPN, EVPN service scenarios include EVPN VPLS, EVPN VPWS, EVPN eTree, and EVPN L3VPN. Let's look at EVPN MPLS and EVPN VPLS in more detail and explore other EVPN service scenarios later. We will cover EVPN VXLAN and EVPN SRv6 in other videos. Let's look at how EVPN is implemented first, starting with the EVPN startup process. Configure EVPN instances and establish BGP EVPN peer relationships on each PE. Then, PEs advertise Type 3 routes to each other. A Type 3 route carries the following information: EVPN instances RD, IP address of the source PE, and MPLS label value. After receiving the routes, each PE knows that other BGP EVPN peers exist and generates a BUM traffic forwarding table. Next, set an ESI on the PE interface connected to a CE and bind the ESI to the EVPN instance. In multi-homing scenarios, an ETH trunk interface must be used to connect to a CE. The ESI can be generated in either of the following ways. Either the ESI is statically set, or the ESI is dynamically generated using LACP. On Huawei devices, EVPN works in active-active mode by default. The single active mode can be configured if needed. After the preceding configuration is complete, PEs advertise Type 4 routes to each other. A Type 4 route carries an ESI value and a source PE IP address. After receiving a Type 4 route, each PE checks whether the ESI value carried in the route is the same as the local one. If they match, the source PE address carried in the route is added to the local ES member list. The ES member list is generated based on the ESI and used for DF election. Next, let's look at the DF election process. In multi-homing and active-active mode, to prevent the CE from receiving the same traffic repeatedly when BUM traffic is forwarded, EVPN introduces the DF election mechanism. Only the device that is selected as the DF can forward BUM traffic to the CE. DF election can be implemented in either of the following modes. The first is DF election based on devices and is the simplest of the two. In this mode, the PE with the smallest source address in the ES member list becomes the DF. The second is DF election based on VLANs. In this mode, the service traffic of different VLANs can be assigned to different DFs, facilitating fine-grained control. In VLAN-based DF election, the following formula is used. V mod N equals I. V is the VLAN ID and N is the number of multi-homing PEs. I is the sequence number of the device that can become the DF in the ES member list. Assume that there are two VLANs. VLAN 10, and VLAN 11. For VLAN 10, 10 mod 2 equals 0. Therefore, PE1 with the sequence number of 0 in the ES member list becomes a DF. For VLAN 11, 11 mod 2 equals 1. PE2 numbered 1 in the ES member list becomes the DF. In this example, the DF on the CE1 side is PE1, and the DF on the CE2 side is PE3. After DF election is complete, PEs advertise Type 1 routes to each other. There are two types of Type 1 routes, per ES and per EVI. The per ES route is used in this example. The route carries an ESI value and a label allocated to the ESI. After receiving the Type 1 route, each PE checks whether the ESI value carried in the route is the same as the local one. If they match, the ESI label value carried by the route is updated to the local ES member list. The ESI label value is used for split horizon and loop prevention. We will describe these functions in bum traffic forwarding later. At this stage, the EVPN startup process is complete. Next, let's see how EVPN learns MAC addresses and forwards traffic when it comes to a specific service process. Assume that CE1 broadcasts an ARP request message to PE1. First, PE1 learns CE1's MAC1 through the forwarding plane and saves it to the local MAC VRF table. Then, PE1 generates a Type 2 route destined for MAC1 and advertises the route to other PEs. The route carries the EVPN instances RD, ESI, MAC1, and MPLS label assigned to MAC1. Upon receipt of the route, PE3 and PE4 update their MAC VRF tables. In this way, CE1's MAC address is learned by the PEs through the control plane. After receiving the route, PE2 finds that the ESI carried in the route is the same as the local one. PE2 therefore preferentially selects the MAC route with the local port 2 as the next hop. In addition, PE2 generates a Type 2 route destined for MAC1 based on the local MAC address information. Upon receipt of the route, PE3 and PE4 update their MAC VRF tables. PE1 does not update its MAC VRF table because it has a better route. After PE1 receives the broadcast ARP request message, PE1 sends the packet to all its peers based on the local bum traffic forwarding table. After PE3 receives the message, it decapsulates the message and determines that it is the DF. Therefore, PE3 forwards the broadcast packet to CE2. After PE4 receives the message, it decapsulates the message and determines that it is a non-DF device. Therefore, PE4 does not forward broadcast packets to CE2, preventing CE2 from receiving the same traffic. Ultimately, let's look at PE2. When PE1 sends broadcast packets to PE2, PE1 finds that PE2 has the same ESI as the local one. This means that PE1 also needs to add the ESI label value 202 into the broadcast packet. After receiving the broadcast packet, PE2 decapsulates the packet and finds ESI label 202. Consequently, PE2 determines that the packet belongs to its own ES. It discards the packet to prevent loops on the access side, implementing split horizon. After receiving the ARP request message, CE2 responds to PE3 with a unicast ARP response message. PE3 learns CE2's MAC2 through the forwarding plane and saves it to the local MAC VRF table. PE3 then generates a Type 2 route destined for MAC2. The route carries the EVPN instances RD, ESI, MAC2, and MPLS label assigned to MAC2. The route is advertised to other PEs. PE1 and PE2 update their MAC VRF tables after receiving the route. In this way, CE2's MAC address is learned by the PEs through the control plane. After receiving the route, PE4 finds that the ESI carried in the route is the same as the local one. As a result, PE4 preferentially selects the MAC route with the local port 4 as the next hop. At the same time, PE4 generates Type 2 routes destined for MAC2. and advertises them to other PEs. Upon receipt of the routes, PE1 and PE2 update their MAC VRF tables. PE3 does not update its MAC VRF table because it has a better route. The MAC address learning is complete. Now, let's see how EVPN forwards unicast traffic based on the ARP reply process. Upon receipt of the ARP response message, PE3 searches the local MAC VRF table for an entry map to the destination MAC1. PE3 finds that the next hops are PE1 and PE2 and must select a path using the load balancing algorithm. This example assumes that PE1 is selected. PE1 encapsulates the message and sends it to PE1. After receiving the message, PE1 decapsulates it and searches the local MAC VRF table for an entry map to the destination MAC address in the original message. The next hop is the local port 1, and therefore PE1 forwards the message to CE1 through port 1. We have just learned the unicast traffic forwarding process of EVPN through unicast ARP response messages. Next, let's take multiple service flows as an example to see how EVPN implements load balancing. Assume that 4 flows are sent from CE1 to CE2. First, CE1 load balances traffic along 2 active-active paths to PE1 and PE2 respectively. Because PE1 and PE2 each have 2 different routes to CE2, traffic is load balanced along different paths. Ultimately, 4 service flows are sent to CE2 through different paths, achieving better load balancing. Next, let's see how EVPN implements fast convergence if a fault occurs. Assume that the link between PE3 and CE2 fails. After detecting the fault, PE3 updates the local MAC VRF table and withdraws CE2's MAC2 route. Then, PE3 generates a Type 1 route and advertises it to other PEs, withdrawing the MAC2 route whose next hop is PE3. After PE4 detects the fault, it becomes a DF and does not discard bum packets. After receiving packets, PE1 and PE2 update the local MAC VRF tables and directly withdraw the MAC2 route with PE3 as the next hop. In this way, service traffic automatically switches to the path with PE4 as the next hop, without requiring any broadcast, implementing fast convergence. In the preceding slides, we have introduced EVPN fundamental in the multi-point to multi-point EVPN VPLS service scenario. Next, let's look at other EVPN service scenarios. We will start with EVPN VPWS. EVPN VPWS is a typical point-to-point service model. Different from EVPN VPLS, EVPN VPWS introduces service IDs and EVPL instances. A service ID identifies an AC interface on the local or remote access side. An EVPL instance is used to associate a service ID with an EVPN instance. PEs exchange Type 1 per EVI routes to map local and remote service IDs. In this way, a point-to-point forwarding path is established. In EVPN VPWS, PEs do not need to learn MAC addresses from each other. EVPN VPWS is similar to EVPN VPLS in terms of the control plane and forwarding plane. EVPN VPWS supports multi-homing, active-active, load balancing, and fast convergence. In addition to the common multi-point to multi-point and point-to-point service models, EVPN supports a special multi-point service model called E-tree. In the E-tree model, there are 2 roles, root and leaf. The root and leaf nodes can communicate with each other, but the leaf nodes must be isolated from each other. Logically, it looks like a tree. This service model is useful in some scenarios. For example, a company wants to interconnect its headquarters and business departments, but wants to isolate the business departments from each other. The E-tree mode is suitable in this scenario. EVPN E-tree can be implemented in 2 modes, per PE and per AC. In per PE mode, the PE can only be a root or leaf node in the same EVPN instance. In this mode, RT mapping between EVPN instances is used to determine whether a PE receives an EVPN root. In this way, the root and leaf nodes can communicate with each other, whereas the leaf nodes are isolated from each other. In per AC mode, each AC interface bound to an EVPN instance can be a root or leaf interface. In this mode, PEs exchange Type 2 roots to advertise the leaf flag of a MAC root. In addition, the leaf nodes exchange Type 1 roots to advertise their leaf label values. Assume that PE1 receives unicast traffic destined for CE3 from an AC interface on a leaf node. PE1 searches the local MAC VRF table and finds that the MAC root carries the leaf flag. As a result, PE1 discards the traffic. Leaf nodes are isolated from each other. Assume that PE1 receives bum traffic from the AC interface of the leaf node. When PE1 sends packets to PE2, PE1 needs to encapsulate the leaf label value obtained from PE2 in advance. When PE2 receives the traffic, it finds its own leaf label value, and therefore forwards the traffic only to the root AC interface, but not to the leaf AC interfaces. In this way, the root and leaf nodes can communicate with each other, and the leaf nodes are isolated from one another. The preceding slides describe L2 VPN service scenarios. As a full-service transport VPN solution, EVPN must support L3 VPN. EVPN L3 VPN is similar to common L3 VPN. On the control plane, EVPN L3 VPN uses Type 5 roots to replace VPN v4 or VPN v6 roots to transmit private IP prefix routes. On the forwarding plane, EVPN L3 VPN also encapsulates packets with two labels. An EVPN label is encapsulated as an inner label to identify an EVPN instance to which the packet belongs. An MPLS label of a public network tunnel is encapsulated as an outer label used in label forwarding. Now that we know the fundamentals, let's see how conventional VPNs on the live network evolve to EVPN. To protect customers' investments in network construction, EVPN evolution adopts the following policies. First, upgrade a few key nodes at the aggregation and core layers to EVPN. In this case, the intersection node of conventional VPN and EVPN needs to support the VPN and EVPN splicing to ensure the normal running of services on the live network. If there are a large number of network nodes on the access side, the network can be gradually upgraded to EVPN to achieve network-wide coverage. Through the preceding slides, we have gained an understanding of the unique advantages EVPN offers in terms of protocol simplification, load balancing, fast convergence, and multi-service transport. Currently, 5G services and IPv6 networks are developing rapidly. EVPN, especially the combination of EVPN and SRv6, will play an important role in network transformation.